recap of confidence intervals in total. First of all, we have a population mean. That is the mean of every single light bulb in the factory. Okay? We take a sample size of n. Let's say we take 50 light bulbs. Okay? We know that the standard deviation of the population, we think, is 12 hours life. Okay? We take a sample of 50 light bulbs and we test them, and we find that the mean life of a light bulb is 600 hours. Now this is a sample mean, which is denoted by x bar. So we've taken a sample mean, we have a population standard deviation, a sample size. Now, if I increase the sample size, what will happen to my confidence interval? It will get smaller. In other words, how confident am I? Because that's only a sample. Now that sample might be right, or it might be wrong. We don't know. We hope that the sample of 50 light bulbs would give us an explanation of, aha, that means the real population is, but it could be up and down, couldn't it? So we use, first of all, a standard error. Now the standard error is sigma over root n, which in our case was 12 over root 50. Okay, now we're going to produce a 95% confidence interval. Now I showed you last time how to use a calculator to actually work out what that value is, but remember that 95% is 1.96. Now I'm convinced that in the test they are going to give you something weird, like an 88% confidence interval, to see if you know how to find that number. Okay, so if you don't remember, look at the video. Okay, now, so 95% confidence interval gives us a Z number. So now our margin for error is going to be plus or minus 1.96 times by 12 over root 50. Now we don't normally write down the margin for error. We normally write the whole confidence interval formula out, okay? But if you're asked what will be the margin for error, that's the margin for error. No, because if you've just been asked for the margin of error, that's what you've got. Now we're going to actually find the 95% confidence interval. So we are going to write down our formula first, which is mu is less than x bar plus z sigma over root n, and is greater than x bar minus z sigma over root n. And we're always going to write that down. And then we're going to chuck all our numbers in. So we now think that the mu is between, remember that the sample mean was 300, was it? 600. 600 plus 1.96 times by 12 over root 50, and 600 minus 1.96 times by 12 over root 50. Okay, and now all we're going to do is wallop those two into our calculator. If somebody could do that for me, that would be really cool. Okay, so what we're saying is that we are 95% confident that the real mean, the whole population's mean, is between this value and this value. Now we'd hope that the real mean would be 600 hours. Okay, so I can make a claim as a company, hey, average contents, average life of my light bulb, 600 hours. Okay, so I could make that claim, but how about making a claim based upon this value? What value have we got in the end? Not one person's pressed into the calculator. Okay. Yep. And the other one, therefore, is going to be 603.33, I think. Okay. So we are now 95% confident that our light bulbs will last between 596 hours and 603 hours on average. Okay, so having taken our sample of 50, tested them until they went bang, okay, got an average of 600. We are now 95% confident that the real population mean lies between that value and that value. And so now I'm going to say average life at least 596 hours. Okay? And that's a safe claim to make now, because I am 95% confident that the average contents is actually between there and there. I'm not going to claim 600, I'm going to claim 596. Yes? Now, of course, this is where they get to. Average life approximately 600. Well, what does that mean? Absolutely nothing. Okay, but that's what we're talking about when we're claiming it for a manufacturing tolerance standard. Okay, and that's how you do confidence intervals.